All right, this video is for AP Calculus and it's on the subject of linearization, which is basically the idea of using a tangent line to approximate a function. But we'll define some other terms here too that will be helpful throughout the course. So the linearization of a function in the region of a given x value and then the meaning of the word differential. So defining some terms. If we have a function curve like this blue or this black function curve here, as long as we stay in a region around some particular x value, then the tangent line is pretty close approximation to the curve itself, right? We've taken like 2 points that are separated let me use colors here. If I'm in the vicinity of an area, I can take 2 points that are on the curve and draw a line between them, which we call a secant line, right? And that's a fixed change in x, which I could call delta x, and a fixed change in y, which I could call delta y. And the average rate of change, that specific phrase, means the change in y over the change in x. But then to take the derivative, what we do is we take those same distances, but we move the points closer together so they're almost on top of each other down here. And then there's a little change in x and a little change in y, like an infinitely small change. I've drawn them here as large, but they're actually infinitely small. And so this delta x becomes what we call dx. And this change delta y, this fixed delta y, becomes an infinitely small change dy. And that little dy dx there, super small, defines the slope of the tangent line, which we define as the derivative. So f prime of x is defined as that. All right. So these things here, this little infinitely small change dx and dy, those are called differentials. You should think of them as an infinitely small change, but they're not zero, and they're close to zero, but they can be different from each other. So for example, let's say that you have a tangent line whose slope is 3. That means that if the differential dx is 1 and the differential for dy is 3, that means however far you move in the x direction on the tangent line, you always move 3 times as much in the y. So it means this function, you could think of it as how sensitive is the y variable change for x variable change. So let's say this is like wolf population versus like the temperature in the forest or something like that. Then that means if the differential dy is 3 and the differential dx is 1, that means for every 1 degree, say C, of increase in temperature change, the wolf population increases by 3 times as much, right? Something like that. So you can think of the differential as a sensitivity, like how sensitive is changes in y, how sensitive are changes in y to changes in x. Okay, but for practical purposes, the dx and the dy are infinitely small changes in the x and the y direction. Right, here's another example specifically. So let's say that you have 30, that's x here is the circumference of a tree in inches, and f of x is the height of the tree in feet. Right, so if the derivative at 30 is 1.5, that means that that for every 1 additional inch of tree circumference, the height goes up by 1.5 feet on average there. More precisely, it means the ratio of the changes in height to changes in radius is 1.5, right? Meaning that whatever change you have in the circumference of the tree, the height will change by 1.5 times as much, and also the units will change from inches to feet. All right, so let's look at some specific questions that are the way AP would ask questions about this concept. Given a function, f of x is x squared plus 2, write the equation of a tangent line to the curve at x is 1, and then use this tangent line to approximate the value of the function at x is 2.2. So what's happening here is we have a function curve. You don't have to draw this, but just to picture it, x squared plus 2 would be this parabola here. We're going to x is 1, right? And we're going to write a tangent line at x is 1, right? So the first goal is to come up with the equation of that tangent line. Okay, so a tangent line, whenever you're asked to find one, tangent line is always of this form. We use point slope form. Y minus y0 equals a slope times x minus x0. Right? So the first thing is we know that we're supposed to be doing this at x is 1, so that means this x is 1 here. In order to find the matching y, we're going to plug that 1 into the function. So that means that since f of 1 is 1 squared plus 2, which is 3, that means we're at the point 1 comma 3. This is y minus 3. So first you have to get the xy pair where you want the tangent line to attach to the function. For the slope, though, we're going to say that this is the derivative of the function so that it's going the same direction as the function. It matches the instantaneous rate of change of the function curve by taking the derivative of f of x, which is 2x, and then plugging in this particular x value of 1 to get that the slope is 2, and then we'll fill that in for the slope. So if we're just asked to find the equation of a tangent line, we could just report this as the answer. It's not required to solve it for y. But then the second part of this problem says to use that tangent line now to approximate the value of a function at 2.2. So now we're going out here to 2.2, and we're plugging in that value to the tangent line, and that will give me an approximation to the real value, which is up here. So there's an error here, but we're being asked to produce the y value on the tangent line as an approximation to the real value. So that means I am going to have to solve this. Right, y minus 3, if I distribute this 2, is 2x minus 2. So that means y is 2x plus 1. And that's the equation of this line. And you can think of that as a function now. So let's define that. Well, I shouldn't call it f because I already have that. So let's just say this. Y evaluated at 2.2 is going to be 2 times 2.2 plus 1. And a lot of times, questions like this, if they're a free response, will be on the non-calculator part. So you have to be able to do simple, like multiplication and division. So this is 4.4 plus 1, so this would be 5.4. So that's the final answer, that f of x, f of 2.2 is approximately equal to 5.4. Right, now, you could, of course, plug 2 into this and find the exact value, but this said specifically it directed us to use the tangent line to approximate the value. Okay, right, this is what's going on. Same thing. We have the change in y, change in x. Right? That's 2.2 is to 5.4. We're just using the tangent line as an approximation. So that's just a visualization of what we just did. Okay, here is another question. Does this approximation over or underestimate the true value at 2.2? So for that, we have to consider the curvature, right? If this function curve, now we can see that it's concave up. If the function curve is concave up in this region from 1 to 2.2, then that means that when we draw a tangent line, the tangent line is going to sit underneath the function curve, and that means this approximation is an underestimate. Right? On the other hand, if this curve had happened to be concave down, then the tangent line at x is 1 would be an overestimate. So it depends upon the curvature of the function curve, right? The line is always linear, but the curvature of the function curve determines what's going on and also which side. Well, actually, I guess it would be the same on either side. So to analyze that, what we would do is, if I didn't have a graph, there's no particular reason we would have to produce a graph. We were given f of x, and the problem is x squared plus 2. We calculated the derivative to be 2x. Now I could take the derivative of that derivative and get 2. And that means that since the second derivative is greater than 0, f is concave up in this region. Therefore, the tangent line approximation, and on the side, I would probably just draw this little thing, concave up, tangent line is below, so at 2.2, we're underneath it, is an underestimate. So we should conclude this as an underestimate because the second derivative is positive and therefore the curvature is upward. Okay, here's another problem, similar. Pause the video if you can, try it, give it a shot, and then unpause and see how close you got. Given this function, f of x is 3x minus x squared plus 4, write the equation of the tangent line. All right, so for that, I'm going to need a couple things. I'm going to need to know the point. This is 2 comma something. To get that, I'm going to plug 2 into the function. So that is 3 times 2 minus 2 squared plus 4, which is 6 minus 4 plus 4, which is 6. Okay? And so that means the point is 2 comma 6. For the slope, I'm going to compute the derivative, right? It's going to be the derivative, which is 3 minus 2x. So the derivative at this point of tangency when x is 2 is 3 minus 2 times 2, which would be negative 1. And then I can write an equation of a tangent line. Y minus 6 equals negative 1x minus 2. There's the equation of the tangent line. Don't have to solve it yet. But in the second part, it's saying that we want to use this tangent line to approximate that function. So this is part A. Part B. Now I'm going to say y minus 6 is equal to negative x plus 2. So y is equal to negative x. And then if I add 6 to this side, that'll be plus 8. And so therefore y at 3, since they're asking me to approximate at this other x, that's going to be negative 3 plus 8, which is 5. So the answer to that is 5, with work shown. And then for over or underestimation, I'm going to take the second derivative. So for the second derivative, that is the derivative of this, which is negative 2. So f prime of x is negative 2. And therefore, f prime at 2 is negative 2 and is less than 0, which means that f is concave down. And since it's concave down, that means that the tangent line approximation will always be above that. Therefore, this approximation is an overestimation of the true value of f of 3. Okay, that's all there is to it. Let's see, a couple more examples, right? Yeah, 2 more examples here. Use the tangent line at x is 0 to approximate the function f of x is sine of x. We'll start with that. Okay, so for part A, let's see, we need f at 0. So if I plug 0 in, the sine of 0 is 0, so the point is x is 0, y is 0. I'm going to need the derivative. So the derivative in general is the derivative of sine is cosine of x. The derivative at x is 0 is cosine of 0, which is 1. And that's going to be the slope of the line. So it's y minus 0 equals the slope of 1 times x minus 0. And so that's just y equals x. This is the tangent line. Sine of x can be approximated with just the function x. And then use this to approximate sine of 0, sine of 0.1, and sine of 0.5. And then for each of these, what's the error? So I think for B and C, let's do these together. And we'll make a little table here. So let's take the x value, and then we'll find the approximation, and then we'll find the actual value, and then we'll find the error. Okay, so they're asking me to do 0. Let's do that first. So the approximation would be using y equals x. So y equals 0. The actual function would be y is sine of x, and sine of 0 is 0, so the error is 0. If we're at the point of tangency, the tangent line exactly matches. Right? But if I were to go to 0.1, then y would be 0.1. This would be the sine of 0.1, which I'm going to go ahead and use a calculator for that. So sine, make sure we're regular. sine of 0.1 is 0.0998. So it should have been 0.1, or that's the actual answer, the error. So maybe I can define the error as the actual, the approximation. We're going to define that as the approximation minus the actual value. So 0.1 minus, 0.1, what is that? The wrong button there. Okay, so the approximation was 0.1, and the actual value for sine of 0.1 is this. So the error is 1.6658 times 10 to the 6658 times 10 to the negative fourth, or that's equal to 0.00016658. So this is very close, but not exactly equal, the approximation. Now, at 0.5, we're going further away from the place where we attach the tangent line to the function, so the error should be larger. Right? So the approximation is simply the x value, 0.5, but this would be sine of a half. And sine of a half is 0.4794. 0.4794 approximately. So the error is the difference between 0.5 and that. 0.5 is the approximation. This is the actual sine of a half. And the error is 0.02057. So you can see what's happening here. We're above, so that means this function is the sine function in the vicinity of 0. Looks like this, right? Right? So it's perfect right here, but then we're approximating with a tangent line. That means that the further away we go, the bigger the error is, and it's a positive because the actual amount is an overestimation for the actual value of sine. Okay, one last example. Use a linear approximation to estimate the given number, and they didn't really state where to center it at, but this is taking the square root of 36.1. There is a convenient x value near there. We do know that the square root of 36 is 6, so maybe we can approximate this at x is 36. Okay. So I could say my f of x function is the square root function, or x to the 1/2. If I want to use a linear approximation, we're going to make a tangent line, which means that f at the centering value of 36 is the square root of 36, which is 6. And therefore, the point is, if I plug 36 in, I get 6 out. That's the point. For the slope, we're going to need the derivative of this function. So that is 1/2 x to the negative 1/2, or 1/2 squared of x. And if I evaluate that derivative at the centering value of 36, where we're putting the tangent line right directly on the function, it's going to be 1/2 times the square root of 36, which is 1/2 times 6, which is 1/12. And then we can build a tangent line, so that's y minus 6 equals a slope of 1/12 times x minus 36. And then I can use that to estimate this given number. So that means y minus 6 would be 1/12. X minus 36 over 12 is 3. I could add 6 to both sides and get plus 3. And now I can use this to approximate 36.1. So this is 1/12 of 36.1 plus 3. Now, that would be hard to do without a calculator, so let's go ahead and just use a calculator. 36.1 divided by 12, and then add that to 3. It gives me 6.0083. 6.0083. So this is what they're asking for. Use the linear approximation to estimate the given number. Now, why would you do that? And you could just use a calculator to find the exact answer. Only because we're being told to do it. All right, so that is the last part. All right, so just to summarize, a linear approximation means that you're using a tangent line to approximate a function. And then it's going to be perfectly matching at the point of tangency, and the further away you are from the point of tangency, the further away the error is going to get, the larger the error is going to get. And you can use the second derivative as concavity to determine whether that error is in a positive or negative direction, if it's an over or underestimation. All right, so that should be it for this video.